So this video covers chapter 14 in the book that we used last year. There's no direct correlating chapter in Zybooks, but this is sorting and searching, which we've already covered a fair amount of already. But we do just want to go over the 4 methods you really need to know, as well as a review of Big O notation and what you need to know specific to the test. So you have this PDF. I would highly recommend that you read this as much as possible and go through it. But the most basic type of sorting algorithm is a selection sort. This one rearranges the elements of a collection so they're sorted in sorting order, and it's usually ascending order, smallest to largest. And the way it works is if I have an array, in this case of integers, I could sort anything as long as I have a way using the compare to method of determining which one should come first. I just start an index at the very first. I'm going to say that spot, this when I go initially through the array, position 0, array of 0 is the smallest element, or should be the smallest element. After I make one pass through the array and put the smallest element there, then I update my swap point and say that now the front of my remaining array is at array of 1, and I shall find the smallest remaining element and put it there. Right, I don't care what the data is in the first spot. All I need to do is go through and find the smallest element in the entire array and move it to the front. And all I do is swap. So I take my 11 and I put it where the 5 is. I take the 5 and I put it at the front. It doesn't matter that the 11 is not necessarily in order. All I care about is that at the end of one pass through the selection sort, the smallest element in my entire array is in position index 0. And I don't care about the rest. Now I then have a smaller array of the remaining items, and I just do the same thing over and over and over again until I have reached the end. Okay. So the selection sorter is fairly simple. You're given an array as a parameter. In this case, it's an integer type. If you wanted to sort other things, you need to make sure you change the type and the parameter in a few other places. All right, I go through the entire array, length minus 1, starting at 0. And I'm trying to find the index value of the minimum position, or the minimum value of my array. So I have a method that returns the minimum position, and it has 2 parameters. The value A, which is you're passing it in an array, and the index where you're going to start. So the first pass through my index, I'm starting from the front of my array. That's my minimum position. I need to go find the smallest integer index and put it at I, essentially. Then I go through and I update I, and I now becomes 1. That's the new front of my array, and I check for the remainder. Once I have identified the index value of the minimum position in my array, I'm going to call the arrayUtil method that you already wrote called swap, which just swaps 2 methods, or 2 indexes, 2 elements in an array. All right, so I give it an array to swap. I give it my minimum position, and I give it I. I is the current front of my remainder of my array, and a minimum position is the index value of the smallest remaining value in the array. Minimum position needs to go into position I. The data at I needs to go to minimum position, all within array A. So minimum position method takes a from, or a starting point, and it takes an array as a parameter. Again, if you're doing doubles or bank accounts or something else, you need to change this parameter as well to make sure the array is the correct type. Integer minimum position, start at your from value, which is pointing to the front of the remainder of the array that you're looking at, the unsorted portion of the array. Loop from there plus 1, because I know my start, and now I want to start checking for smaller data, so it's redundant to check my current smallest, which I just set here. I need to start 1 more, which is why up here I started at length minus 1, so that I don't overrun the end. Well, I is less than my length of my array, I plus plus. If the data value at array index I is less than the data value at my currently supposed minimum position, reset my minimum position to equal to I. Go through the remainder of the array, and at the very end, outside the loop, return the minimum position value. Once I've determined the index value of the minimum value of the smallest element in the array, I then call swap. So this creates my random array. And I have a swap method, which just like any other time, takes a variable, an I and a j, a start and an end. I need to temporarily store the data that's in index A of I, and then, so obviously this needs to be the correct type, the type of the array. If it's an integer array, this needs to be an int. If this is a bank account array, this needs to be a bank account. So I temporarily store I take the data value that's in index j and I put it into I, and then I reset j to be what my temp was. And then I am done swapping it. Okay. Profiling, hopefully you've actually done this and run it on your own, but you just create a stopwatch that starts and stops when told to, and then can calculate the difference in milliseconds based on the clock time that has elapsed in between. It's irrelevant, but when we run stopwatch timer, create a new stopwatch object, call the start method, then call my sort method, and then stop my the timer, I'll figure out how long it took the sorter to sort. Now if I plot the data for, let's say, n, the number of elements in my array of 10,000, 20,000, 30,000, 40,000, 50, and 60, you're going to get a graph that looks relatively like this. Okay, these numbers in milliseconds will be different on your computer. Hopefully your computer is a lot newer than when this book was written, and they should be a lot faster, but the scaling progression will hold true. Okay, and the way you're going to read this, so this is half of an ellipse, so this is an elliptical path, so this is a quadratic. So you notice that every time you double the number, it takes twice as long, roughly. So if I double, it takes 4 times as long. When n is 2, that is to say I have doubled it, the profile of a quadratic means that it will take 4 times as long. N squared, 2 squared is 4. And I can look at that when I go from 10,000 to 20,000, I've doubled it. I've gone from 720 to 780 to 2100, which is essentially a jump of 3, but if we did it enough, it'd average out to closer to a jump of 4. And then if I look at 2,000 to 4,000, again doubling it, I can see that it's much closer. In fact, I had to multiply essentially 2,000 by 4 to get 9,000, and it's roughly a 4-time jump. Okay, so when I have doubled my value, if I look at the difference between 30,000 and 60,000, that's about a factor of 4 again, pretty close to a factor of 4. So that means that if I have multiplied my n value, or the number of elements in my array, by 2, the runtime goes up by a factor of 4. So that tells me this is an n squared. Now, there's a whole lovely mess of calculating. You can see here the actual way of calculating the values, but we don't really care. All right? You're not going to have to calculate the values. You need to know that selection sort is O of n squared. Okay? And again, the reason why we only care about the largest term in any sort of given efficiency algorithm is because that's the one that counts the most. When we're talking about large numbers, let's say n was 1,000 or 2,000, then 1/2 n squared is 500,000 or 2 million. The next one, 5 has n minus 3, comes up to be like 2 or 3 or 4,000. So when I'm comparing that against 2 million, it's irrelevant. So I can just drop it all out. All right. So I only care about the number of times, or number of things that have to happen, number of commands that have to be run, for each number of elements that there are. Okay, so I have big O notation. The number of visits is O of n squared. This is convenient shorthand. All right, and so that's not particularly very efficient. But again, it's relatively easy to write. So you should know that selection sort is an O n squared algorithm, doubling the data set. So when I put my n value in, but I put in a change to get the answer. So I don't put in n is 10,000. I don't say 10,000 squared. That's not going to work. But the time spent on sorting, the order of the growth is n squared. So that means when n goes up by 2, the entire time is going to be a 4-fold increase. If I went up by 6, or let's say I went up by 3 squared would be a 9 times increase. Okay. So I've got a couple common big O growth rates. You don't really need to know the names, but you need to know the couple that apply to certain types of algorithms. Okay. you should you should know insertion sort is an O(n) squared. And you should have a rough idea how it works, but it's not one of the big ones. Merge sort is the one other sorting algorithm that you really need to understand to be able to write, identify, modify, and work with. Okay? The idea behind merge sort is that if I'm trying to combine a list, and I have half the list sorted and the other half sorted, it's then very easy to sort the remainder. Because all I have to do is compare just the front element of each one and decide which one needs to go into my ultimate final list. So if these are my two halfway sorted lists, and this is my ultimate final one, so I have two lists of 5 that are sorted, and I want to make one complete, unified, combined sorted list of 10. Well, I just have to compare the fronts of my arrays. So first I compare 5 and 1 and say, all right, 1's smaller, it goes in the spot. 1's gone off my list. Now I have 5, and the front of the right side array is now 8. Well, that means 5's got to go next, so I put the 5 down. I remove the 5 from my list, and now I have 9 and 8. So I compare 9 and 8, and I decide that 8 has to go. So now that's gone from my list, and the remainder of my list is 11, and the front of the other one is 9. So I will decide that 9 has to go, remove it from my list, and now my list starts at 10 and at 11. I compare 10 and 11, and I decide that 10 needs to go, remove it from my list. My list is now 12 and 11, and I continue and I stack the entirety of my array. Okay? This is a recursive solution, because what my base case is going to be is that it is infinitely easy to sort a list of 1. A list of 1 is already sorted. So as long as I can break up any given list into individual chunks of 1, I can then merge sort them relatively quickly. So my base case, if the length of my array is less than or equal to 1, that saves me from crashing if I get an array of 0, I just return. I'm done. Otherwise, I take my array and I cut it in half. I'm going to make a first array and a second array. The first array is half my length, and the second array is my length minus the length of the first one, so that catches any odd numbers where it doesn't divide easily. Then I just sort the first one, I sort the second one, and the very last thing that I do is I merge them. Now notice I have sort, and I have sort. Anything that I do where I call a method inside of the same method is recursive. So this doesn't end until I have broken it all down to arrays of length 1. At which point I then start merging the first one and the second one back into my final array A. Okay, so here's sort, cut it in half, keep chopping up smaller and smaller and smaller, and then merge. So I'm given 2 arrays of my first and second, which are at this point my sorted arrays, and I'm going to merge them into one final array A. So the index of the first array is 0. The index of the second array starts at 0, because remember these are 2 independent arrays, so they both have index values of 0. And then the next open position in my ultimate final array is also starting at 0. So while I loop through, my index value of first is less than the length of my first array, and the index value of second is less than the length of my second array, saying there's still data in at least one of them, keep going. If the data at I first is less than the data at I second, which is essentially the first data position of my second array, then I need to add it to my current array and update first, so I skip. Otherwise, if the first element in the second array is smaller, I need to add it to the next available spot in my final ultimate array A, and I need to update the index of second, so it now skips over that one and leaves the next. Then, while I first is less than the length, update to copy the entries. Okay, and then this is just a demo of it. If we analyze the merge sort algorithm and plot it out, we get this very flat, shallow curve with a much more gradual sequence of adding values. So when I double 10, it doesn't go up, it only goes up by a factor of maybe 2. And when I go up 4 times, it only goes up by a factor of 4. So it's a much slower growth rate. And then when you evaluate it, you can do all the math if you want, but again, you don't care about the math. All we care about is that it is a logarithmic where'd I go? It is an n log n algorithm. Merge sort is an O of n log n. You need to have that memorized. Much more slowly than n squared. So again, here's where I need to compare two different ones. If I have doubled n, that is, so I would put 2 in here, then the approximate growth rate is log of 2 times 2. Okay, that's how you would use this equation. Quicksort is the way is faster. There's a pivot point. You should have a rough understanding how quicksort works. But the two you really need to understand are selection and merge. All right, searching, finding data. The fastest one to write, the easiest one, although not very efficient, is the linear search, where you just start at the beginning and you go through until you find a match. All right. Over time, it would be n divided by 2. We could say that you're going to get the value half the time in the first half of your array, and over time that would hold true. But efficiency algorithms are worst case, and so we don't care about any constants. So overall, linear search is an O of n algorithm. That is to say, however many elements you have, that's how many search comparisons you're going to have to make. And if you double the size of it, it's going to double the length of time that it takes us to run. So it's very simple. You give me a value to look for and an array as a parameter, and I just loop through the entirety of that array. If the data at I equals the value I'm searching for, return I. It returns the index value in the array of where your data you're looking for is stored. Otherwise, return -1. I return -1 because obviously that is not a valid array index under any condition, and that would tell me immediately that the data was not found. Okay. However, O of n is not, like I said, particularly efficient. Binary searching, which we've already talked about and you should have a little understanding of, is a much faster way. The one trick is that the data has to be in sorted order. Otherwise, this will never work. And again, the way it works is I look at the middle, and I look at my data. I say, are those two the same? If they are, I'm done. If my data is larger than my middle value, then I can immediately ignore all of these options and only search on the remaining ones, the larger ones, in which case I'll again look at the middle and say, am I high or low? Do I need to look on the left side? My value is smaller. Or I need to look at the right side? My value is bigger. Okay. So to search binary, you're given an array. You're given a low value and a high value and the value you're looking for. Initially, your low value is 0, the far left side of your array, index value of 0, and your high value is the last valid index array, or length -1. If low is less than or equal to high, that is to say I haven't hit an array of 0 yet, calculate the midpoint. If the data value at my midpoint equals my value that I'm looking for, my search, return the midpoint index, I'm done. If my midpoint index value is less than my search value, then that means I know it's in the left half, or the lower value half of my remaining array, and I can ignore the rest. If that's true, then my midpoint needs to go up. My high point needs to stay where it is, and I'm not changing my search value at all. This is also recursive. Else, go the other way. Keep my low point the same, reset my high point to be the one less than the midpoint, and look on the left side. When we profile this, binary search is O n log n. And you can also calculate this by hand. So let's say that n is 100. How many times would it take to run? Well, if n is 100, then O log n is, what's the value? It's about 7. But you could cut it in half. You could say, well, the first pass, there's 100 elements. Second pass, there's 50. Third pass, there's 25. Fourth pass, there's 12. Fifth pass, there's 6. Sixth pass, there is 3. And then I'm down to 1. So 7 times to run the whole thing. Estimating the runtime of an algorithm, have a brief understanding, but you don't need to know that for too much about it. Again, you need to know the big O notation for selection sort, linear search, merge sort, and binary search, and you need to have an operating understanding of how they work. Now, when you're writing an actual program, and you can do this on the AP exam, but it's not tested, the arrays class already knows how to sort. It's a method of quicksort. So if I have an integer array and I import the arrays class, I can just sort it. If I'm going to use an array list, I need to import the collections class, and it also has a sort option for me. If I'm going to do a search, I can do a binary search on an ordered array. The nice thing is it returns -k -1, where k is the position before where the elements to be inserted. So if I have a 3-integer element array of 1, 4, 9, and I search for 7, it's going to return -3. So that is to say, at position 2, right before position 2 is where this value should be. Position 0, 1, 2, position 2 is the 9, it should become right before position 2, which is true in this case. All right, comparing objects. If I want to use arrays and collections, or if you're going to do it yourself, you need to use the compare to interface. All right, compare, except for the arrays for and the collections, it's going to be a parameterized, almost like an array list, of comparable t, where I'm going to have a compare type. So for instance, I could have a class called country, and I could use comparable country, and then I just call the compare to method on the other. It might look something like this. Public class country implements comparable with an interface type, with a type. Public int compare to country other, return however you want to compare them. Now, this is not tested on the AP exam. The standard compare to method, which you could still write without the comparable interface, without the parameter types, would still work. Just know that compare to then has a parameter of an object type, and your first step is to cast it back into the actual type. Now, if you're using the parameterized one, you don't have to do the cast, you can just use it. But you do need to remember how to use compare to. Alright, so I would read the rest of the chapter and go through it, and again, particularly spending time reviewing selection sort, merge sort, linear or sequential search, as well as binary search.